Join and change the audio is fine. One join it.
They're probably, yeah, they're going to join from a room at some point once they figure out how to get on the Zoom. We don't do Zoom. We only do Google Hangs.
What? Teams.
Oh, okay. So that's even worse. Trying to get a Microsoft product to work on a Google machine. They'll join 15 minutes in when they figure it out. I wouldn't be surprised if a bunch of them joined from their phones because that's the only way they can get it to work.
Okay, we'll get started. It's my pleasure to welcome Dr. Thomas Wenisch. He's the Director of Engineering in the Network Infrastructure Group at Google. He's based out of Madison, but lives in a global team with over 100 engineers. Around 20 of them are actually based in the city. And he's responsible for Google's production networking communication stack, including remote procedural calls and West bypass networking stack. Previously, he has been a professor at University of Michigan at Ann Arbor, and even before that, he received his PhD from CMU. He has received many awards, including the prestigious ACM Sigurd Maurice Wilks Award for contribution to memory persistency and energy efficient systems. His past research mostly focused on computer architecture, with particular focus on the server and data center systems, memory persistency, multiprocessor, multi-core systems, performance evaluation, and medical imaging. With that, so over to Tom. Talk about it.
Thank you for the kind introduction, Arka. And thank you everyone for coming today. It's been almost 15 years since I visited IISc. So it's fun to come back to Bangalore after all of this time. I suspect I was actually in this very room 15 years ago when Govind hosted me. So it's really a pleasure to be able to come join you again. And hopefully, now that I have a team here in Bangalore who I look forward to meeting many times over the coming years, we'll have an opportunity to continue to meet with folks here at IISc and build a relationship with Google. So as Arka said, I'm a director of engineering now at Google. Previously, a professor in computer science at Michigan, focusing on computer architecture. And today I'm going to talk about a topic that connects to some of the research that I was doing sort of at the tail end of my time at Michigan, but that is very strongly connected to what we still care about a great deal at Google, really trying to build low latency, large scale distributed systems. And some of you may recognize this title, Attack of the Killer Microseconds. This is not my title. That's the title of a Communications of the ACM article that was written by Luis Barroso, Dave Patterson, Partha Ranganathan, and Mike Marty, all very well-known luminaries in the computer architecture field, but that really articulated this challenge of how do we build distributed systems that are very efficient, very highly utilized, very cost effective in a microsecond scale world where lots of I/O and lots of storage accesses are happening in single digit microseconds. And really the observations that we'll talk about in this talk are how this reality of microservice-based cloud systems design is quite different from a world where we only have spinning disks and accessing storage takes milliseconds, or a world where we're only building single big iron database style applications and all of the data we want is in memory and only mere nanoseconds away. And so the killer microsecond, as you can see, this is the wonderful artwork, this one from my student, and this is my pathetic attempt over here at a killer microsecond that's really undermining the efficiency of our systems. Okay, so a little bit of background. Online data intensive services is a term that we coined in some previous paper. I don't remember exactly when. For the class of workload that is a real-time interactive workload like web search or social media processing, but where each individual interaction that a human user would have with the system has to process potentially terabytes of data. But because it's an interactive system, we're targeting millisecond scale response times. And so the canonical example of this would be web search. But of course, there's many other things that now fall into this class. Again, social media processing, ad serving, and now increasingly even machine learning model serving. Interactive large language model serving is, of course, sort of the new hotness in industry. And it really does kind of fall into this class of online data intensive services with the added wrinkle that now we need to deal with GPUs and TPUs and all these other accelerators. And what's important is to try to process terabytes of data with millisecond scale response latencies. You can't do that on a single system. The only cost-effective way of doing that is to shard the computation over many thousands of systems, many thousands of accelerators in order to actually get response times over the amount of data that we need to process. And so a lot of the intelligence in the design of these things comes in how do we go about sharding the work over a large number of computers. And since these are interactive services, there's a human waiting at the other end of the internet for a response, tail latencies are extremely critical. So we want to have tight bounds on 99th percentile tail latencies. Now, if we go back 20 years, many things like Oracle database and so on were really built as monolithic software systems, where sort of one binary would pack together lots of different functionality, security, data management, processing, and so on, would terminating HTTP connections, doing encryption, and all in one single application. However, this is very difficult to scale because sometimes the computation demands of the various pieces of functionality in such a system scale independently of one another and scale in different dimensions. And so even though you can scale up a monolithic application by stamping out many copies of that same binary and sharding your traffic, it's not a very efficient way to build a global scale system. And so instead, what has happened over 20 years, this is not really a new idea, is that most of these internet scale systems have moved towards a microservices architecture where each of these individual functionalities, terminating the web connection, managing the storage accesses, performing some kind of security services, performing inference over a machine learning model, are moved into independent microservice applications. And then these microservices, which communicate over a remote procedure call over the network, can now scale independently. And in the aggregate, we can end up with a much more efficient system. However, the amount of processing that's now being done in each of these microservices is much less, potentially only a few hundred milliseconds or even a few hundred microseconds worth of processing. And there's a very complicated communication graph where you might have a very deep tree of microservices that need to talk to one another, potentially sequentially, all in the critical path of an interactive web query that we want to finish in, say, 100 milliseconds, 200 milliseconds. And so what that means now is that the latency of these RPCs and the latency of activating an accelerator becomes critical, both on the average, so that we, on average, can maintain the throughput and complete the application processing, but also the tails of any of these communication hops become extremely critical because they're additive on the critical path. So how do we, and you can see these pictures here, these pictures are from a 2019 paper. Those are pictures of the microservice interaction graph of several very famous large-scale distributed systems, right? And so you can see there's lots and lots of little bits and pieces talking to one another to make one of these large-scale internet services work. Okay, so why do we want low latency? This might be kind of obvious, but we want to build and design distributed big data without requiring extremely expensive exotic hardware capabilities. We want to be able to use relatively inexpensive, relatively replicable, relatively scalable hardware infrastructure to build things like web search, BigQuery, MapReduce, Spanner, but we really do need to optimize to make sure that the end-to-end latency of these services is acceptable for interactive use, okay? And we make these things cost effective, as I said before, but through resource disaggregation, through spreading the computation and sharding it over a large number of machines, through spreading disks over many machines, through spreading RAM over many machines, and scaling each of those resources independently based on how much we need. But the degree to which we can perform that kind of disaggregation, spreading data across the network, is limited fundamentally by the communication latencies between the systems, which of course is ultimately limited by the speed of light. But we'd like to come as close to that as possible. And what has changed over, let's say, maybe 10 years, perhaps 15 years, is that the distances between systems and the distances between computation and I/O have drastically shrunk relative to, say, when I was an undergrad. So now we have accesses to persistent memory, for example, at the scale of single-digit microseconds, or within a single rack or within a single sort of block of accelerators, at rack scale within a data center. You might be able to access another system or tens of systems within 5 microseconds. And in addition to worrying about the latency of these things, we also have to worry about how much CPU overhead are we consuming in these interactions over the network. How expensive is it for me, from a CPU perspective, to have one microservice talk to another, right? So we care both about low latency and about the CPU occupancy of the communication between these bits and pieces. Now, the reason disaggregation is so important, and the reason we would like to have things interact over the network rather than in monoliths where perhaps we'd have to replicate a data set over and over, is that disaggregation lets us have fewer copies of critical data sets in memory, and memory is very expensive. So rather than having every sort of, imagine web search in a monolithic world, you could imagine each web search binary has to have the entire web index in its local memory, and it can do some number of web search queries. Well, then I would have many copies of the entire web search index in memory. What I'd rather have is one copy of the web search index that's accessible over the network and shared by a lot of workers who each process individual queries. And that's not exactly how it works, but that's the mental model you should have about why disaggregation is so important, because it allows us to eliminate replication and rely on communication over the network instead. And so it really, the key is that you're scaling compute and data independently, you're scaling all your hardware resources independently, and that enables better distributed algorithms, better search results, better ads, and so on. Then, of course, this is a computer architecture talk, and you can't have a computer architecture talk in the last 20 years without having something that says end of Moore's law. And so, of course, end of Moore's law, like anything else, motivates some of the problems that we are now facing as systems designers. Cores are not getting faster. When I wrote this slide, I claimed that we're not going to keep doubling cores. It turns out we're still doubling cores somehow. I guess chiplets and all these other weird things have allowed Intel and AMD and others to continue to give us more and more cores. At some point, that's going to run out of steam. There's only so many atoms left in the transistors. So eventually, that red sentence will become true. But certainly, single-thread performance hasn't been improving for a long time. And so that has a couple of implications. And one of them is very obvious to anyone who's been following what's been going on with NVIDIA's stock, for example. There's an enormous trend towards hardware specialization, accelerators, hardware offload, trying to rely on things besides single-thread performance of an out-of-order von Neumann processor, which isn't really all that well suited to something like machine learning inference or machine learning training. And we see accelerators in all sorts of other places as well. One of the most very successful ones is encryption offload, as an example. And I'm talking mostly about low latency data center networking, right? Talking about microservices talking to one another via remote procedure call over the network. But the same kind of challenges arise when I want to do low latency asynchronous activation of an accelerator, when I want a CPU task to ask the GPU to perform some inference. Well, that has to go over PCI. That's also a microsecond scale communication interface. The second trend that we see from cores not getting faster, and eventually we don't get more of them, is that we need more parallelism at the system level, at the data center level. We have to bring more chips to bear to solve these problems. And Amdahl's law really matters, of course, and Amdahl's law will always limit the maximum speed up we can get through parallelization. And so you have to focus on that sequential part of anything that you're trying to speed up. And that calls critically for lower latency communication, or communication will become the serial bottleneck, and you can throw as many computers as you want at it, it won't get any faster. So, going back, 14 years, part of what the Madison, Wisconsin office of Google was asked to think about, when Larry Page sort of supported its creation, is why can't we have RPCs at the speed of light, right? Yes, we're fundamentally bottlenecked by the speed of light, but the software overheads are putting us pretty far away from the limit of how fast electrons can or photons can transfer over the optics in a data set. Well, so we're trying to meet that challenge. The problem, of course, is that low latency is really, really hard, right? It's not that trivial to actually shave all of the overheads so that our communication protocols really are no more expensive than the time it takes photons to move over wires and links. So this is not a new problem. Like supercomputing style applications have been trying to figure out how do we get massive scale GPU clusters and CPU clusters to perform various kinds of high performance computing operations for decades, right? Supercomputing is a very old field. However, when you think about the kind of applications that I'm talking about, online data intensive applications, and when you realize that the hyperscale operators like Google and Facebook and Microsoft, they have a highly multi-tenant, highly heterogeneous system with many different applications, and a lot of the cost efficiency comes from co-running these different applications together in a shared infrastructure. And most of the things that allow supercomputing to go fast are really incompatible with that multi-tenant shared infrastructure paradigm. So, for example, in the supercomputing world, you would typically have a link-level flow-controlled fabric, such as InfiniBand, which is lossless and has stiff flow control and basically kind of assumes that only one application is running at a time on the fabric. And the moment you'd have any performance interference from two applications that are not sort of jointly optimized together, the entire performance of the network will fall apart due to tree saturation and pauses that cause innocent bystander traffic to kind of get stuck, just like you're driving around here in the city. Also, the software fault model of supercomputing applications is really fundamentally different from the fault model that we assume in something like a Google data center. The fault model for supercomputing is typically you checkpoint once a day, and if anything goes wrong anywhere, the entire application recovers to the checkpoint, and we start again. We don't attempt to tolerate any subcomponent failures while the application is running. That's not going to work at Google scale, right? Things are failing all the time, both in software and in hardware. And so this shared everything environment means that you will always have interference, you will always have unpredictable queuing. Queuing latency is kind of fundamental, and that's one of the biggest sources of tail latency that we need to combat in our systems. And again, these are businesses, and cost efficiency is critical. And so in order to drive down cost, computers cost a lot of money when you buy them at hyperscale. And we need to operate them at the highest utilization that we can in order to derive the most value from the massive capital infrastructure cost that's invested into these systems. And it's not only capital cost that matters here. As you well know, data centers consume gigawatts of power, and so the operational costs are also critical. And not only do we want to operate at high utilization, but we want to take as much advantage of low power modes and other energy saving features as we can. And yet those features again destroy tail latency, because now you have to wait for something to wake up, you have to wait for a circuit to be energized, and there's just fundamental constraints on how fast that can be done. So, here's a kind of cheeky slide for, how can you waste a really fast data center network, right? So, with remote direct memory access technology, and if you can do some sort of co-location of stuff in a data center, you really can achieve communication with just a couple of microseconds between two machines that are relatively near one another. But the moment I start adding additional mechanisms on top that, of course, make it much easier to program and build systems, I very rapidly add massive software overheads over this latency here that's pretty close to what you can get from the wire. So, remote direct memory access is a read or a write operation where you're directly accessing the memory of a remote computer over the network. And so really all of the software only happens on the initiator side. The responding side is entirely in hardware. If we start going to a send-receive model, more like a supercomputing application, now we have software on both sides. Well, I've just doubled the overhead. And now if I imagine I have to wake a server application thread, because it has to respond and figure out exactly how I'm going to deal with a particular request. Well, now I have a thread dispatch overhead, and in Linux, that's somewhere in the vicinity of 5 microseconds. And then if I'm going to have an interrupt-based networking protocol, because I want to be efficient and I don't want to, simply sit there and, watch for packets to arrive all the time, well, now that's another 5, 10, 15 microseconds, depending on how unlucky you are. And then by the time you add a remote procedure call stack on top of that, well, it turns out there's quite a bit of software involved in marshalling and unmarshalling data, in matching, you're doing tag matching to match a request to a specific handler, find that code, fire it up. And, we also have the overheads of things like TCP, because of course packets go lost in these networks and you have to retransmit. And so, even though speed of light is, not too much less than this, by the time we have, real software, well, actually, it's even worse, right? Because there's queuing, there's interference, maybe something else was running on the core and you have to wait in line. And so, in the tails, these latencies are even worse. Yeah, go ahead.
So I just wanted to actually get a clarification. So when you talk about this communication using remote procedure calls and other things, you compared it to supercomputing, but I actually wanted to get this straight. So the communication is with machines or systems which are co-located in the same data center. They are not geographically distributed, are they?
So the question is, for these RPC-based systems, are they co-located in the same data center or are they geographically distributed? So, so the answer is actually both. Something like web search consists of certain steps that are geographically distributed. And then it also consists of steps where a bunch of microservices that are co-located, at least in the same city, maybe not exactly the same network fabric, same building, will coordinate with one another. And the vast majority of the communication is intra-data center. But if you think, you come to some load balancing system that looks at, where are you, how have you come over the internet, and looks at the load of various Google data centers and has to decide, well, which web search backend am I going to dispatch your request to? So that's all RPC based. And that is RPCs over the wide area network. But then once you get to a Google front end, which is sort of the thing that terminates your web connection, that then will internally within that cluster orchestrate communication to all of the microservices that collectively implement web search. And again, it's many of them because it depends on exactly what kind of query you're giving. So both, but maybe there's more to your question.
Yeah, that's right. The second part of my question is that amount of data that is being communicated by these what's the order? Like, is it kilobytes or is it?
Yeah, so the question is, what is the order of the size of the data communicated by RPC? And the answer is that the vast majority of RPCs are very small. On the order of kilobytes. There's some amount of overhead from RPC framing and so on, but typically these are requests of relatively small pieces of data. Even the vast majority of RPCs, it turns out most of the data that's moving around in the data centers are accesses to and from storage, so reading and writing either disk or solid state disk. And there, the requests are tiny. The responses are some block size based on sort of how we organize our file systems. But again, at most megabytes. There are exceptions. I mean, if you're going to stream a video, there might be like a streaming RPC that opens a connection and then continuously spoon feeds data through that connection over a very long time. So there are paradigms where you might move very vast amounts of data in one RPC, but normally it would be kilobytes for the vast majority.
So my question is that do you want to actually optimize your RPCs for these two dimensions and then based on that size or based on that geographically located or not, or you want all your RPCs to be optimized, irrespective of what?
Yeah, in the context of this talk, the ones that matter are the small ones that are local to a data center. Once you're going over the wide area network, you probably already lost. And so, if you think, like I said, the end-to-end objective for web search might be, say, 200 milliseconds. Well, that includes the internet. The internet is half, or something like that. And so now some of that 100 milliseconds is going to be consumed getting to the right data center. But from there, then we want things as fast as possible, so that we can meet that overall sort of global target for your query. Okay, yeah. So all of this was just motivation to the problem statement. Attacking the killer microseconds, right? And it's this observation, again, which I can claim no credit for, that microsecond scale I/O creates a fundamental tension between performance and productivity, and we need new ideas in hardware and systems in order to mitigate latency and to find ways to drive utilization up without driving queuing latency up and still allow us to build infrastructure with lots of little hops among different microservice style components that are responsible for the end-to-end latency. Okay, so how does this, let's relate this back to computer architecture, okay, and sort of, well, what does it mean for someone who wants to build a computer? And so the first observation, all of you have taken computer architecture courses, have learned many, many advanced techniques that are astonishingly good at hiding nanosecond scale stalls, right? If you think about everything you learn about caching, out of order execution, memory level parallelism, simultaneous multi-threading, prefetching, these are all examples of techniques that have come from the hardware computer architecture community. And in the aggregate, what they've allowed us to do is basically make it a memory access look like it's almost free, right? Memory is somewhere between 50 and 200 nanoseconds away. And as long as those main memory accesses are infrequent enough, maybe 1 in 1,000 instructions or 1 in 500 instructions, then we'll be able to hide all of the time it takes to get to that memory device by doing other processes, by doing other instructions in the meantime. And the beauty is that we're using concurrency to hide latency, right? Instruction level parallelism, but it's completely transparent to the programmer. We didn't have to do anything in our C++ applications in order to get all of the memory access latency to be entirely hidden by these hardware mechanisms. And so the programmer gets the wonderful abstraction of straightforward ordered loads and stores. Of course, it's still pretty hard to program correctly, but that's much better than a universe in which we'd have to organize all of that instruction level parallelism by hand. Now, if we go to the other end of the spectrum, let's suppose we think about millisecond scale stalls, like what would happen when you access a spinning disk. Again, this is a solved problem since decades because modern operating systems have been designed with the idea of hiding millisecond scale stalls in time in mind. So again, we rely on parallelism, but now we do IO level parallelism. If the disk is going and fetching one thing, I move on to the next transaction in a transaction processing database and do the computational work for that transaction while I'm waiting for the disk to get to the data that I want. And in the meantime, I'm going to queue up additional in-flight operations to the disk, and the disk provides massive throughput, even though the latency is quite poor because we have to wait for the disk to physically spin. However, again, the key point is that even though parallelism is a solution to hide the latency, that parallelism is again transparent to the programmer. You don't have to do anything to get applications to context switch when you go read from a block device. It just doesn't. And yes, you need to make sure you have enough concurrency and you have enough transactions in flight, but as long as you have lots of threads, you can have lots of disk accesses in flight. You don't really have to do anything else. The latency is hidden for you. However, as I said in some of the motivating materials, I/O, offloads, and microservices give us stalls that are in the microsecond regime. Think. And it turns out that puts us in a donut hole where neither our hardware techniques nor our operating system techniques are able to hide those stalls. On the hardware side, once you get past 200 nanoseconds, it's simply impossible to be able to hide all of that latency because we can't make an out-of-order processor with a speculation depth and an out-of-order window big enough to hide that kind of latency. And on the operating system side, it's far too expensive to do a context switch. The context switch costs almost an order of magnitude more than these stalls. So we have, microsecond scale stalls from disaggregated memory, CXL attached memory, non-volatile memory devices. We have 10 microsecond scale stalls when we go over the network. We're using, high-end flash. If we have a multi-tier service, one of the biggest challenges is mid-tier microservices, which essentially are, taking user requests in and then sort of breaking them apart and routing the requests to other microservices that might deal with shards of the data. This server right here does very little processing itself. And so the I/O overhead, the overhead of in and out communication dominates over everything else. And another challenge, of course, is that because of queuing, we can't operate these things, full bore at 100% load. We need to operate them at, say, 50% load, or we're going to be sort of climbing the exponential part of the queuing latency distribution. And if you have a system at 50% load, if you reason about, well, what does that mean at nanosecond scale? Well, what it really means is you have bursts of compute followed by bursts of doing nothing. And for a 200,000 QPS service at 50% load, the average idle period between requests is, again, single-digit microseconds, tens of microseconds. And so we also need to deal with the microsecond scale dead periods in between periods where the system is doing work. So, the premise of my call to arms here is that we need hardware and software mechanisms to hide microsecond scale latency. So, sort of what are the contours of the solutions that we want? Sort of what are the constraints? Why is this hard? Okay. One of the things that makes this really hard is that we still have to think there's a programmer involved, and we need to make it easier for programmers to write programs. And it turns out even I, as a director at Google, can write file access code that looks like the synchronous one on the left here, where we fopen and then we fread. But the key is that these are blocking calls. We don't proceed to the fread until the fopen is done. That, of course, means we're incurring all of the latency if we can't context switch and do something else. Now, of course, there are asynchronous programming models. And you can look this exact same set of operations here. This code, I think, is Windows code to do the same thing. I randomly copied and pasted it off the web. And obviously it doesn't even fit. I think it goes down again like another page about the same size. Massively more complicated to do exactly the same thing, but now I'm not incurring asynchronous. All right, programmers want this. Okay. So synchronous programming models are wonderful. They maintain the model of sequential execution, and the magic that makes the synchronous programming model easy to use is that all of the state associated with a particular request or a particular context lives on the thread stack that's associated with the thread that's executing. And so the management of that thread local state is sort of automatic. You don't have to do anything about it. The C language has done it for you. And so there's less code, it's easy to understand, and it's more maintainable. And this count words operation that counts the number of words in a document, is relatively simple. We call read document index, and then we call read document, and then eventually we call count words in a string for the entire document. And all of us can understand this code relatively easily. How can we maintain this synchronous programming model in a world where we have microsecond scale stalls? Okay, there are really two options. One option would be to spin and stall and simply wait on the synchronous instruction until that microsecond stall completes. Okay, so a thread that's doing that operation sits there and waits for the accelerator reply, waits for the message to come in over the network, which enables really low latency dispatch to the reply. We know exactly which thread is going to continue execution. It's sitting there waiting. The moment the data shows up, we don't have to wait for any mechanisms to tell us, hey, your data has arrived. So we have no hardware interrupt processing overhead. We're polling for the arrival of our result. There's no uncertainty as to where to continue execution. We're going to run in exactly the same hardware context as where we issued the request. All of our state stays warm in the cache. There's low risk that the operating system is a jerk and comes along and deschedules us because we're hanging on to that execution context. The problem with this model is that while we're waiting for that microsecond scale IO, we're not doing it. We're literally just burning energy. And so the CPU does no useful work. And in a world with simultaneous multi-threading where you have two hardware contexts sharing a single core, spinning is actually very disruptive to the hyperthread peer, and it's certainly wasteful of energy. And fundamentally, the maximum degree of parallelism we can have, the number of outstanding requests, if each of them requires holding on to a hardware context, is limited by the number of cores. Okay, so this gets low latency, but it trades off efficiency for it. What's the other end of the spectrum? This is what sort of the spinning core model looks like in the common case. You have a single CPU and it's sitting there and spinning and doing all the work. Let's start this animation again. You can see, CPU 0 there is happily spinning away, going faster and faster. But when you write an application this way, you can see all the other CPUs are just kind of standing around and not really helping. They're cheering on while CPU 0 does all the work. And somehow the shirt comes off somewhere in there. I don't quite understand how that works. And then eventually we overheat and it crashes. So that's the spinning model. The other option is to let the operating system come along. So when we get to one of these synchronous IO points, we're going to have that thread block and wait for an OS interrupt before we continue, and then we can give away that execution context so the CPU does other useful work. Now, this is not free. Just asking the operating system to come along and swap in another execution context actually has a fairly high compute overhead relative to our microsecond scale IOs. You have 5 to 10 microseconds of direct latency overhead from the context switch itself. So you have hardware interrupt overheads when you end up wanting to process the reply over the network. And then once you receive an interrupt saying data has arrived, well, it probably goes to the wrong place because we don't know who this network packet is destined for. And so the soft hierarchy mechanism in Linux just wakes up a random core, whichever one happens to have the network receive queue. And so that means we might have to move the data that arrived over to the CPU that's ready to continue the work. And we have OS scheduler overheads, well, which are fast in the common case. But again, the OS scheduler can be a jerk. You should view it as your adversary, and it wants to charge you a millisecond or more every time you ask it to do something. In addition, there are indirect costs of a context switching model. You have cache state getting thrashed in a study from, I think this is IBM, a long time ago, but that adds maybe only 5 microseconds, but could add a millisecond, a slowdown to the code that continues executing after the data arrives. As I said, the OS scheduler is your enemy. And also, it's not even necessarily clear, like, should I resume on the same CPU that issued the request? Should I resume somewhere else? Should I wait for that CPU to become available? The scheduling problem is actually quite challenging. There are a lot of interesting publications, and I actually have more citations later, on a model where instead of time multiplexing all the cores, we dedicate some of the cores in a space multiplex fashion just to receiving all of the I/O and then playing switchboard, deciding exactly how to dispatch the work back to the original threads that initiated the requests. One of the examples is Shinjuku. I think that's already almost 5 years old, but there's been a lot of follow-on work in that space. Okay, go ahead.
So, are you only talking about OS scheduled context switch, or are you also talking about hardware context switch?
Here, I'm talking about OS scheduled context switch, and one of the potential, solutions that we could bring to bear would be hardware assisted context switching. Maybe we have more execution contexts on a core than actually can co-schedule on it. So not simultaneous multi-threading, but sort of multi-threading with swapping. And certainly there have been research publications, including I think one of my PhD students at some point, did some work on how could you multiplex a larger number of execution contexts onto a thread that can only execute 2 or 4 at once. So that certainly is one of the kinds of solutions that I'm trying to suggest. But again, I'm in industry now. I don't show up and tell you the solutions. I tell you my problems. You're supposed to tell me what the solutions are. Okay. So, totally different direction, right? We want synchronous programming, but it turns out at Google, to first order, what we actually resort to make things like web search work is asynchronous programming. Okay, so we'll write, event-driven programs which run to completion and don't rely on context switching and, POSIX threads as the mechanism to encapsulate a user's request. However, this is extremely difficult. It's extremely difficult to teach people to do, and it's extremely difficult to get right because the control flow of the program becomes obfuscated in a nest of callbacks and lambda expressions and function pointers, and all of the state that is associated with a request, instead of being magically managed for you on a stack, now has to be explicitly tracked in a heap allocated data structure. So, if I want to do async count words, well, okay, there could be errors. I need to have the index and the document, and I also need to know when I've finally got the count, like what is the next code that's supposed to run. And so the first step for async count words, I do some setup. I have to allocate the state. I have to point the done callback to like the next step in the process. And then I can call my async read document from the index and, go off and move on to the next request. And I have to pass it all this garbage because all of the state has to explicitly be moved sort of from continuation to continuation in order to proceed with the processing. And then so if we go to the next step, eventually the data comes back from whatever storage device, and I had said the callback function was read document index done. So that's going to get called with the state that I had explicitly allocated on the heap. And now I have to, check if there was an error. And all I'm doing is just invoking another asynchronous step where I say, okay, now I've looked in the index, let me go get your document. And yet another complicated C++, how many people remember how to do this off the top of their head? Standard bind, read document done, make sure all the function signatures are correct. And again, we're passing through that explicit state object. All right, and then eventually we have a third callback for read document done. And, again, check for error. And all we're doing there now is invoking count words and string, again, asynchronously, and passing that to yet another done callback, whatever called us to begin with. Clearly, this is much more difficult to understand than the exact same functionality I showed you in 5 lines of code room. And we actually haven't really solved the killer microsecond problem. All we've done is like freed up the CPU so we can move up to onto the next thing. And we're responsible for maintaining all the concurrency of all of those synchronous, concurrent user level requests that we're trying to process at once with explicitly managed state. Okay, so here's an example of some of the research directions that I have worked on and that many others in the research community have worked on towards solving this problem. we could use, instead of traditional sort of kernel-based I/O blocking system calls, we could move to this library OS style model as one of the many models that have been proposed, or microkernels, where we're getting the kernel and the kernel scheduler out of the critical path of interacting with I/O, and instead using user space libraries and shared memory communication, talking directly to our I/O device. And so in fact, precisely this model is what one of my teams at Google works on. It's actually the team that's in Madison, Wisconsin. And of course, we're not the only people to have pursued this kind of solution. There are many, many academic studies. These are all sort of, almost a decade old in some cases. But many people have come up with creative ideas of rethinking the I/O architecture of our operating system. How can you get to near optimal latency and throughput? Well, hardware PCI has advanced, and we now have hardware I/O virtualization, like single root IOV, user level queues and spin polling, like the mechanisms we use in Snap, which I'll talk about in one more slide. And we also have I/O devices that are smart enough to do zero copy data transfers. So for example, your network card can be smart enough to deliver the payload of your machine learning training application directly to the GPU without first having to drop it into the system. Go ahead, Oscar.
So one of the goals that you mentioned that you wanted to use not an expensive hardware, but more like engineering hardware, right? But when you have this reasonably capable the network card and so on, does that actually matches with that goal?
So the question is, I said we want commodity cheap hardware, and yet, we want advanced hardware capability. And yeah, that is a challenge. Certainly, we want the hardware devices to be cheap, and so we want inexpensive commodity network cards to support these kinds of virtualization features. Unfortunately, cost in this space is driven by ultimately chip area. The bigger the chip is, the more expensive it is, right? I mean, yes, there's business stuff on top of that, like margins and things that I don't understand. But hardware I/O virtualization does not have to massively increase the amount of silicon on a chip, and we're buying these things at enormous scale. And so it really is the cost at the manufacturing level that drive that. So this should not be too expensive. Now, where it starts getting complicated is when you start talking about smart NICs and things like Amazon Nitro. There's a whole computer in your I/O complex with lots and lots of cores. Those are very expensive. What is the right model there? That is yet another talk that is at least twice as long. That I probably can't say in public. Okay, just one slide on some of the work we're doing at Google. Again, this was published at SOSP 2019. Our work on user level data planes. So Snap is the public name for an infrastructure that Google built internally that's very similar to Intel's data plane development kit. So it's a spinning core model for interacting with network devices and for controlling CPU scheduling. And most of the things that use Snap within Google are packet-oriented services. So they do things like encapsulation and decapsulation, firewalls, that kind of thing. However, one specific use case for the Snap framework is this infrastructure Pony Express, and the Pony Express team reports to me, which completely throws away traditional TCP-based networking and builds an entirely new networking stack that you can think of kind of as a software-defined network card on top of direct access to the hardware device, so raw Ethernet packets out, and shared memory communication to client applications that are asking for high-performance networking services, right? So applications will use shared memory to speak to our Pony Express microkernel process, which within it speaks directly to the hardware interface of the network card with no context switch, no privilege level change, and taking advantage of all the features that we can to get things like zero copy and so on. So why is this? And this, by the way, it's on almost every data center computer that Google has. It's not quite 100%, but that's a very large number of computers, as you might imagine. And we use it for both cloud infrastructure and for internal low latency applications. And it accounts for a significant fraction, I don't think I can tell you the number, of our intra-data center network traffic. But the goal is that eventually all storage traffic will be using, so that's true and from disk or SSD, will be using this infrastructure. Why are we doing this? Well, the microkernel paradigm allows better coordination, scheduling. That code is all lock-free. We're very careful about how concurrency works. The spin polling and zero copy gives us low latency. We don't pay for interrupts. We can get very high throughput. And we have isolation in the hardware between the network processing stack, which now hopefully gets better branch prediction locality, better cache locality. It's not competing with the application to run in the same execution context. And one of the very big deals about this is a user space stack. We upgrade it every single week without stopping the applications that are using it. So with open connections and with data flowing, we completely swap out the entire implementation of Pony Express across the entire fleet every week. And for the most part, no one notices. And so that gives us excellent velocity in order to rapidly develop and deploy new features. For example, baking intelligence directly into the network transport. I have to have numbers and bar graphs because, again, it's an architecture talk. So again, these are all taken from the SOSP 2019 paper. So this shows you a comparison of latency. I think this is a single rack latency, kernel TCP using a busy polling paradigm, so you get rid of interrupt overheads. Pony Express doing two-sided send-receive style operations where both sides have to do work. Pony Express doing busy polling, so the same kind of spin polling optimization here where we're not waiting for interrupts. And then finally, a one-sided RDMA operation where we're emulating what InfiniBand does. And you can see, okay, this is worse than the number I showed you before for what's theoretically possible with hardware RDMA. Right? Hardware RDMA really should be close to the speed of light plus some switching overhead. But we're within a factor of 2 in a fully software-defined system that can basically work on any network. Similarly, from a throughput perspective, it turns out that TCP, it's actually pretty hard to get high throughput on a single TCP connection. Whereas with one core, in the snap paper time frame where we have 100 gigabit network cards, we could get pretty close to full line rate with a single core, in an inter-rack context. And of course, these numbers are all higher now because we have newer hardware since then and things have gotten more efficient. Okay, so the last thing I'll say is I'll give a little call to arms, and I'll talk a little bit more about Google and Bing. So, my premise and the reason I've come to speak to all of you researchers today is because, there's still a need for research in this space. And we need to engage more people in the systems community, the operating systems community, the hardware community to think about these problems. One approach might be to make asynchronous programming easier. And in fact, that is happening. So people who follow C++ development may be aware that the latest revision of the C++ language has coroutines and async await as a new programming model that potentially makes asynchronous callback style programming much more accessible, but probably still not as good as doing all the callbacks yourself. Maybe we can do what Govind was suggesting and imagine hardware-assisted context switching so that, from software's perspective, there are many, many more execution contexts than the hardware actually supports. Better language support, maybe explicit management of cache state, so you don't have this cold start problem when you swap in a new context. And as I said, languages are continuing to innovate. We could put more and more hardware threads into our system. So to date, all of the really successful systems have been at most 2 hardware contexts per core. You could imagine doing more than that, and certainly we have kept getting more and more and more cores within a system, up to hundreds of cores nowadays in the largest chips you can buy from AMD and Intel. But maybe we should be borrowing ideas for GPUs where we have, switch on miss or warp style scheduling. There are lots of wild and crazy ideas that maybe can be brought from the CPU world from the GPU world to the CPU world. We might be able to do a better job on the reply path, matching replies to the CPU that was requesting them. So hardware support for routing I/O completions, intelligence on ground whether it should stall for that same core to continue execution or start the execution somewhere else. And again, should we do something smart with cache state, like protect it from eviction while the I/O is outstanding, or restore it in some fashion from some secondary cache? And so, there's lots of ideas and lots of papers. And of course, I, in industry now am asking, well, can I make it work at scale? Can I make it work, with zillions of computers? Can I make it work in the face of faults? Those are all very hard challenges. All right, so I'll conclude the technical part. General purpose low latency is hard, but it remains important, and it's important continues to grow, and it is very tightly coupled with, what is going on in the machine learning world with machine learning inference and serving systems that now need accelerators in the critical path. And attacking killer microseconds really is a multidisciplinary research topic. Before I take additional questions, let me just power through a little bit of an introduction to Google in Bangalore. So this is some part of the wonderful skyline of your city. Google has an enormous presence in India. The first presence was actually established all the way back in 2004 with a variety of sites. But we have had absolutely explosive growth, and in particular in Bangalore and Hyderabad in the last 4 years. There's a lot of business functions, but also an enormous amount of engineering across all of Google's product areas that takes place here in India, including in my organization. And just to give you a sense, here in Bangalore, it's very tech focused. So nearly 6,000 people in software engineering or related roles now, and then a couple of smaller business operations. But it's really a tech heavy site. Very young site, lots of recent graduates joining. So it's really had very exciting growth. And just to give you a sense of that growth, look, so this is where we started in India in 2004 with 7 employees, and just look at the we had all this sort of relatively flat, and then in 2019 just before COVID started hitting, Google really decided to supercharge its India strategy because of the enormous talent pool that's available with the many strong universities here, and hiring has just exploded along with the growth through the pandemic, and so now we're up to nearly 6,000 at this site. Actually, this data is from February 22nd. I'm sure it's already wrong, and even in my organization, we intend continued growth here in Bangalore. So it's really a strategic initiative on Google's part to make a big bet on India. And so actually, I was sitting this morning in Kyoto East, which is, I guess, in Whitehall, right? Whitefield. Okay. So really wonderful building. And then, there's a bunch of other buildings being built around the city. So 4.6 thousand seats. Notice that we already are out of space for everybody. So some people are multiplexing, but of course, we're going to be building additional space, another 10,000 seats. And so we anticipate total headcount in Bangalore will be in the vicinity of 15,000 in the not too distant future. So with that, let me thank you all for coming and listening to the talk, and I welcome any further questions that you have. Go. Yeah, okay, so the question is, my research just directions are all suggesting software solutions when I said software can't solve the problem, right? So I'm a software guy now. You can get pretty far with asynchronous programming if you're really trying to, willing to try hard enough. I mean, web search works, despite the fact that it faces these microsecond scale delays. And so I guess I know how to make great low latency systems, but it's very expensive and it requires very senior engineers. And I want to make it cheaper. And the way to make it cheaper is to make the programming more accessible. And so that's why a lot of what I was suggesting focused, on how can we make the power of asynchronous programming more accessible. Because at the end of the day, only God can change the speed of light. And sadly, no matter how much money we have, that constraint will always remain. Yeah, go ahead.
I have a kind of a vague comment I want to respond on this. So you talked about asynchronous programming being harder and becoming better, but still harder. Are there any thoughts on using other productivity languages?
Yeah. So the question is, are there thoughts on using higher productivity languages to try to make it easier to address these challenges? And I think the answer to that is unequivocally yes. We have Go that was developed at Google, which is intended for writing these kinds of systems. I know the Rust community has heated up a lot recently, primarily motivated by security, more so than making low latency accessible. But and you see things like async await and coroutines as emerging in multiple programming languages as a more accessible paradigm to come very, very close to what is possible with truly asynchronous programming. But the vast majority of lines of code at Google are still C++, despite what the US White House tells us that we're not supposed to program in C++ anymore. And I hire mostly C++ programmers. We do have some Java, some Go, some Python, but that's still where their truly high performance systems tend to be written. There are exceptions. Some user-facing systems are in Java.
My comment is more that you use these high productivity languages, programming them, and then translate it to.
Yes. So one strategy that Govin's suggesting is that we could write in a higher productivity language and then lower it to some representation that is ultimately asynchronous. Google has tried that a couple of times, and many of those attempts have. And in a smaller group, I'm happy to complain about some of them. I have Google colleagues on the line, so I have to be careful what I complain. Other questions? We still have a few minutes there. Go ahead.
I remember correctly, the student Akshita did some work in this.
Yeah, so in fact, yeah, Akshita Sriraman, who is from Bangalore and was one of my very last students, I think she was second or third to last, and is now a faculty member at Carnegie Mellon. A lot of her thesis was motivated by a talk I gave at some random conference that was essentially a variant of this talk. And so her thesis was entirely about addressing the killer microsecond problem, and in particular focused on accelerators, you know, the accelerometer paper that she did in collaboration with Facebook was focusing on, can we build analytic models to help us reason about the performance of, you know, asynchronous systems that are built out of a bunch of accelerators.
The question is, what is the impact of such work in this?
Yeah. So the question is, what is the impact of, for example, Akshita's work? So one of her earlier papers was on the observation that depending on the load that you have on a CPU, when the load is low, you would like to execute an RPC handler on the same CPU and avoid the thread dispatch overhead through the operating system to pass the work up to a different CPU. However, as you continue to increase load, eventually you get to the point where you're going to overload that CPU and have queuing delay. And so there's a tipping point where the optimal thing to do is pay the overhead of the dispatch to essentially kick the execution of the RPC handler to a second core. And essentially the first core becomes only a dispatcher. And so this load activity in what threading model you should use and where the sort of optimal tipping point is was the subject of our very first OSDI paper. I don't remember the title. I'm sure we can find it relatively quickly. And that kind of approach, we definitely use exactly those kinds of mechanisms in various infrastructure in Google. It's a problem we have to solve over and over again, because you always have this question: should I run a handler inline or should I dispatch it? And knowing the right answer depends on a lot. Depends on load, depends on how long the handlers are, depends on variance, how predictable they are, depends on the cost of sort of the offload to a different core. And so it's a very difficult problem. Yeah. So the question is, why are we using RPC? RPC was really motivated by compatibility, especially protobufs in particular, if you're familiar with that technology, is about version compatibility. And so, if it's one company, why are you wasting all your time and why are you paying all this overhead for RPC? Well, so, maybe the answer isn't technical, but it's a very real answer nonetheless. There are thousands and thousands of teams involved writing thousands of binaries that collaborate in these microservices, and they all version independently. They all upgrade at different times. They have different life cycles. They're managed by different teams. And so, in fact, protobuf at RPC really is a critical enabling technology. Otherwise, we would never, from an organizational perspective, be able to build a large-scale application, because you would have to sort of stop all of Google, bring it down, and then bring up a new version. And of course, we have to operate 24/7 everywhere. We can't drain our systems. We have to upgrade them incrementally. And so, really, you're correct. RPC has massive overheads relative to what I showed you for RDMA, but those overheads are performing necessary functionality. And in fact, there are many other things. So it turns out RPC is also, since it's the communication fabric that allows applications to be stitched together, and since essentially all applications are using RPC to interact, it's also the single place in Google's infrastructure where we can enforce various policy objectives that the company has. As a specific example, maybe many of you have heard of the DMA 5.2 regulation in the European Union that just recently is, I think, coming into effect in like a few days or something like that. And part of what DMA 5.2 requires is that your data cannot be moved from one product within Google to a different product. Well, the mechanism for enforcing that is by observing the RPCs, labeling the RPCs with which product they belong to, and labeling the RPCs with whether you have opted in to provide permission for that data sharing or not. And if we didn't have RPC, if every application did its own thing, or if we're all based on RDMA, I don't think we would have been able to meet the requirements of the European Union regulations. So there are reasons why it's slow because it has to be. It's not slow because we don't have great engineers. We have fantastic engineers. You should all join us.
So I have a question. So not exactly related to the reporting, but you mentioned like how the disaggregation is work. And there are many disaggregation technologies, particularly on the memory side, like itself. So, how does Google or looks at the implications of CXL or CXL moving Google's point of view for disaggregation?
Yeah, that's a fantastic question. So the question is, how does Google or industry more generally think about upcoming disaggregation technology, CXL being an example of a technology that's being introduced for memory disaggregation? I have a lot to say on this topic, and I'm happy to say many things when I'm not being recorded. But it's certainly of interest. It's certainly of great interest. I think we participate in the CXL consortium. We're just now starting to get server chips that actually are capable of CXL. And it remains to be seen. Certainly for capacity expansion, it's obvious that CXL is quite promising because you can hang much more total aggregate memory capacity off of CXL attached, memory bus style thing than the number of DDR channels I can pack into, a server style processor, because the number of DDR memory channels is fundamentally limited by the number of pins. And the number of pins is limited by the size of the chip, and the size of the chip is limited by yield and physics. And so I can only have so many pins, so many channels, so much DRAM attached. And so I think having more memory attached to a single system might enable kinds of disaggregation that were not possible before. And so CXL could be an enabler for that. I think there are problems with the specifics of CXL, and so I'm happy to sort of expand on those.
Processing more than what actual data processing.
Yeah, so the question is, do we spend more time in the network than we do in data processing? There are individual applications where that's the case. The specific application where that comes up is in key value serving. So one of the teams that I'm responsible for is something called ClickMap, which there's a SIGCOMM paper about it, I think 2019 or 2020, which is a key value store that uses RDMA implemented in Snap Pony Express. And there, the server side processing for a minimum sized key retrieval is in the vicinity of 200 nanoseconds, right? And that's all network stack. There's nothing else. So for an application like that, yes, networking comes to dominate. Now, for most applications, that's not the case. If you're going to go talk to Gemini and ask it to, do some inference for you, the processing time on the, the TPU or GPU that's running a model greatly dwarfs the networking overheads. However, in the aggregate, the total fraction of Google's CPU spend on networking, sort of data center tax. So Partha Ranganathan has this data center tax paper, and it quantifies, the amount of stuff that is in overhead, marshalling and unmarshalling, encryption, malloc, there's a heck of a lot of memcopy, soft IRQs in the networking stack, RPC. I think if I remember the data in that paper, it gets into the vicinity of 20% of all CPU cycles are that overhead as opposed to business logic. And RPC in particular, one of the reasons why I'm so excited to be responsible for the RPC team is that it is also a substantial fraction. Again, I don't think I can tell you the exact fraction, but it's a large chunk of that data center tax is RPC. And so that means that my team and my people have enormous leverage for cost savings. If we make even, a small savings, every if statement in the RPC stack has a measurable cost to Google. And so, getting rid of an if statement is an optimization worth considering. Okay, time for one more, or? Yeah, so the question is, are we going to have congestion due to the number of PCI lanes being limited? And as you noted, I already said DDR channels are limited by pins. The number of PCI buses you can have is also limited by pins. Now, because we have a very different kind of SerDes, the data rates are different. The scalability of PCI, there are PCI switches. You can hang larger and larger CXL mumbo jumbo.
off a single PCI bus. Certainly it's going to be bandwidth constrained, but you can get a pretty big PCI complex. I actually think the limiting factor on the scalability of PCI really is the fault model. So PCI has no notion of false domains and partial failures. If any part of a PCI complex fails, the only thing you can do is crash the machine. And that fault model is fundamentally unscalable. The more individual chips I put in a system, the higher the MTBF is. And at some point, PCI just isn't the right solution. And if you look at how we build data center networks, we assume any particular node can be down, any particular link can be down, any particular switch port could break, and any particular packet can be discarded. And that is really the fault model that you need for scalability. So I think PCI might be scalable enough for some of the things we were talking about, and there are new PCI standards on the horizon that will raise data rates, and we can get a fair number of PCI lanes in a system, but it's not magic, right? And at some point we need something better. Okay, well, thank you again.
Yeah, thanks a lot.